Hey guys, Miss Marusik here, and in this video we're going to talk about titration calculations involving a weak base combined with a strong acid. Now in our previous video we looked at the combination of a weak acid with a strong base, and in those calculations we used an acronym of NDSE to solve the problems: net ionic, dilution, stoichiometry, equilibrium. We're going to use that same acronym here on these problems because again we have a weak strong combination. However, the difference is that now we have a weak base instead of a weak acid, and so we're going to see some slight differences in the reactions that we write for each of these titration steps. So with that said, let's go ahead and jump into our problem. We're going to consider the titration of 100 milliliters of 0.1 molar ammonia. Ammonia is a weak base. Not only is it not a group 1 or 2 hydroxide, but they also give us a Kb value for it over here. We're going to combine that with 0.2 molar HCl, which hopefully we know hydrochloric acid is one of our strong acids. So once I see I have that weak strong combination, I know on my calculations I'm going to be using that NDSE setup. So on our first calculation, they want us to determine the pH of 100 milliliters of 0.1 molar NH3 ammonia before we add any HCl at all. So this is just the calculation of the pH of the base as is. And we know since it's a weak base, I would need to do a Rice calculation to do that. Now I went ahead and put this whole entire calculation worked out for you on here. And the reason why is because this is something that we've done earlier in this unit. I would have my Rice table here with my ammonia reacting with water to give the ammonium polyatomic ion and hydroxide. So that's how I'm going to get my OH out of this base. So then I would plug everything into my Kb expression. Once I solve my Kb expression, that would equal X. Here, X is representative of hydroxide ion concentration. So once I take the negative log and get my POH, I can subtract that value from 14 to get my pH. And what that does is it gets us a starting value of the pH of 11.128. The reason why we need this piece of data is we need to know where our titration curve starts. And so that's why we needed to do this calculation here. The substances present in the solution in a significant amount would be NH3. However, I would have a little bit of these two ions, the ammonium and the hydroxide, because a little bit of that ammonia did dissociate into those ions. All right, our next calculation. We'd want to determine the pH when 25 milliliters of 0.2 molar HCl has been added. So here's where we're starting to titrate our substances together. I'm starting to put the HCl into my ammonia. And so the first thing I need to do in my NDSE setup is get my net ionic equation. Now, in our previous video, we saw in that problem that they asked us to write out the net ionic before I started. Here I'm going to have to come up with that net ionic in the context of the problem. So just keep that in mind that sometimes you have to do that as part of your work for these steps. So the first thing I would want to do is I would want to think about, well, what would ammonia and hydrochloric do when they interact with each other? And hopefully we remember that ammonia being a base would accept an H plus from the HCl. The HCl being an acid would donate an H plus to the NH3. And so that would leave us with the ammonium polyatomic ion, NH4 plus 1. And then I would also have chloride ion remaining from the hydrochloric once it donated that proton. However, I have to remember that hydrochloric is technically a strong acid, and so therefore I should be breaking it apart into ions. Now notice what happens here. The chloride ion ends up as a spectator on either side of this equation. So I don't know if you remember from our previous video, whenever we were addressing the substances present in the solution in a significant amount, remember one of the things that's always present there is our spectator ion. So off the bat, I know that chloride ion is going to be present in the solution once it's all said and done because it's not going to be involved in these upcoming reactions that we're going to talk about. So with that said, once I cross off the chloride on either side, that would result in the net ionic equation we see here. The NH3, the ammonia, plus the hydrogen plus 1 ion, making the NH4 plus 1 polyatomic ion, the ammonium polyatomic ion. So what's the next step in NDSE? That would be a dilution, right? And so that means I want to conduct a voom-voom calculation for both of my two reactants to figure out what their starting concentrations would be. Now, to get my final volume here, remember I had the 100 milliliters of ammonia, but I'm combining it now with 25 of the hydrochloric acid. That's going to get me a final volume here of 125 milliliters. So now when I do these voom-vooms, I'm going to say, hey, for the ammonia, we had 100 milliliters of 0.1 molar. I want to figure out my volume at 125 milliliters. That gets a molarity of 0.08 for the ammonia. I'm going to do the same thing for the hydrogen. Now remember, all of the hydrogen is coming from this HCl, and there's only one H in there, and so therefore whatever this information is for HCl would also be my information for the hydrogen ion. And so therefore, I would have 25 milliliters of 0.2 molar of the hydrogen to start off with. I now want to figure out what the new molarity would be at 125 milliliters. And that would get me a new molarity of 0.04. So now, what's the next step in NDSE? That would be stoichiometry, right? So this is where I want to do a rise table that's a modified one where I'm just looking at stoichiometric ratios. I'm not doing any kind of equilibrium. This is going to be a complete making products process here. So whoever the limiting reactant is will totally go away. So I would want to look at my two reactants and ask myself, well, who's the limiting reactant? Well, these are in a 1-to-1 ratio, and I had less of that hydrogen ion here than I had of the ammonia. And so therefore the hydrogen ion is the limiting reactant. And so what I would do is I would subtract that value from both of my reactants, but I would also add that amount to my product over here. And so at the end, that gives me 0.4 molarity of NH3, none of the hydrogen ion, and 0.04 molarity of the NH4 plus 1. Now, the eventual goal is to get to pH, right? Well, I just eliminated the one thing that could have gave me pH, right? I could have used hydrogen ion to calculate pH, but that is all gone. And so what that means is that now I need the last step in my NDSE, which of course is equilibrium. These ions here that are present are going to do an equilibrium. Now, technically, both ammonia and NH4 plus 1 could participate in an equilibrium. But remember, if we have some of the parent reactant left, I always want to use that as my starting place in my equilibrium reaction. If there was no NH3 left, then I could go and start off with the NH4 plus 1. And we'll see that here in a little bit. But for now, I want to start off with NH3. And so this would be an equilibrium rise table that I'm doing here. I know NH3, when I put it into water, as we've said earlier, is going to make NH4 plus 1 and hydroxide ion. This is the same equation that we saw on part A of this example. However, this time I'm starting off with 0.04 molarity of the NH3, but I'm also starting off with 0.04 molarity of the NH4 plus. And so then I would fill out the rest of my rice table. I know this is equilibrium rice, and so therefore not all of this is going away, only some of it. I know this is going to gain a little bit, and I know hydroxide's going to gain. And so now what I would want to do is I would want to solve my Kb expression. Now I didn't rewrite the Kb formula. I'm using the same Kb formula that I used up in part A. So that would be my two products here, the NH4 plus 1 times the OH over the ammonia, the NH3, which equals my Kb, which was 1.8 times 10 to the negative fifth. So then I say to myself, ooh, that looks kind of complicated to solve. Ooh, but I see that Kb is small, and so I know when it's small, I can typically ignore these changes that are occurring here. And so therefore, once I finish solving for x, I get 1.8 times 10 to the negative fifth. Well, if I think back to what I'm trying to solve pH here. Well, now I know x, and X is equal to hydroxide. So now I can come over here and I can say, hey, if OH is 1.8 times 10 to the negative fifth, I could take the negative log of that and get my POH. And then I can subtract that from 14 to get my pH, and that gets us a pH of 9.256. Now, I want to talk about something for a minute because I intentionally picked a very specific spot on the titration curve with this data. When I gave you this data, you might have noticed that you had exactly the same amount of your original weak base as you had the conjugate acid. These two were equal to each other. That only happens at a special point called the half equivalence point. And when those two are equal, what happens is that my X here, or my OH, ends up equal to the KB. You notice the 0.04 divided by 0.04, that all canceled, and so X equaled that KB. That only happens at the half equivalence point. Okay, so keep that in mind. That was how I knew I'd reached this point. However, something else interesting happens at the half equivalence point. Okay, because the OH was equal to the KB, that means the POH was equal to the PKB. However, I don't really care about POH all that much. What I care about is pH here. And what happens is if I know I'm at the half equivalence point, pH will always equal the pKa. Now, I know some of you are thinking, well, I didn't have the Ka. How could I get that? Well, don't forget, Kw equals Ka times Kb. So if you actually recognized here that you were at the half equivalence point, what you could have done is you could have said, oh, well, I know pH equals pKa. You could have taken this Kb, solved for your Ka, and then take the negative log of it, and that would have been your pH. And you would have saved yourself a little bit of time. So what I want you to kind of understand is that with some of these problems, if you kind of recognize you're at a particular point in the titration curve, there might be a sneaky way to solve that step. And we're actually going to see some more of that in a later video. Okay, let's go up to this box right here and fill it out. So obviously we know our pH. Let's talk about the substances present in the solution. So we're going to have chloride ion present, which we know that's our spectator ion. I'm also in a significant amount going to have both ammonia, our NH3, our weak base, along with its conjugate acid, the NH4 plus 1, the ammonium polyatomic ion. And because I'm at the half equivalence point, those two amounts were equal. Okay, that was how I knew I was at the half equivalence point even before I figured out that the Kb equaled X. I saw that the NH3 and the NH4 plus were in equal concentrations. Before you get to the half equivalence point, you should have more weak base. After the half equivalence point, you should have more conjugate acid. And so we'll talk about that a little bit more when we get to our titration curve. Now, you technically have a very small amount of hydroxide present, and that was what caused the pH to be basic. However, if I was drawing a particle diagram, I would not show that hydroxide. It's too small to be shown. I would show these other substances, though, present in my solution. All right, let's go ahead and flip the page. All right. So here, we want to determine the pH when 50 milliliters of 0.2 molar HCl has been added to our ammonia solution. So again, here's where I'm adding my weak base to my strong acid. And so we know that we need to think through the NDSE acronym. So starting off with the N, the net ionic, this is going to be the same net ionic that we constructed on the previous page, where the NH3, our weak base, is going to combine with the H from our strong acid to give us NH4 plus 1, that ammonium polyatomic ion. The next piece in this step would be the D, the dilution. And so I'm going to figure out what my total volume would be. I would have 100 milliliters of the ammonia, but now I've added in 50 milliliters of the hydrochloric. And so that gets us 150 milliliters of our total volume. And so now I want to do my voom calculation for each of my two reactants. So I would have my NH3 at 100 milliliters of 0.1 molar, according to our beginning part of the problem. I'm now going to figure out what that molarity would be at 150 milliliters. And that gets a molarity of 0.0667. I would then do the same thing for the hydrogen ion. Remember, the hydrogen ion comes from the hydrochloric, so I just use hydrochloric's information here. 50 milliliters at 0.2 molar. I want to figure out what the molarity would be at 150 milliliters. And so once I do that calculation, I again get 0.0667. Now, at this point is where I would do my S step, my stoichiometry step of my rice table, where I'm looking at who the limiting reactant is and understanding that that's going to get all used up. But notice what happens here is that I had equal amounts of both NH3 and the hydrogen ion. And so therefore, they're kind of both the limiting reactant here. They're in a perfect stoichiometric ratio. Now think about where that would happen at. That would happen at our equivalence point. So off the bat here, I know that once those are equal to each other, that they're going to perfectly cancel and neutralize each other out, and I'm at the equivalence point. So even though I did not do a stoichiometric calculation beforehand to figure out where my equivalence point was at, I could very easily tell that once I started getting into the NDSE calculation. All right, so what that means is that all of the NH3 and the hydrogen ion are going to totally go away. And all I'm left with here is the NH4 plus 1, the ammonium polyatomic ion. So then I'm like, okay, well, do I have information to solve pH yet? Well, all the hydrogen went away, so that doesn't help me. So what that means is that I need to do the next step of equilibrium. I need to do that E piece of NDSE. However, normally we would use our reactant to figure out our equilibrium. However, that's all gone here. And so therefore, I am going to have to use my product. However, think about what kind of product this is. NH3 was a base, and this is its conjugate partner, meaning this is a conjugate acid here. Now think about what an acid would do in solution. We know we're going to put it with water, but if it's an acid, then that means I should be forming either hydrogen or hydronium ion. So be very careful when you do this next step. We want to remember that that NH4 plus 1 is a conjugate acid. So when I put it with the water, what's going to happen is it's going to donate its H plus to the water. So that leaves behind NH3. But then look what I end up making. I end up making hydronium ion here. Now remember, hydronium ion is the same thing as writing hydrogen ion. I'm just showing it attached to water. And so this is what I'm going to use to eventually do my pH calculation. However, before I do my pH calculation, I first kind of need to solve for X. And so to do that, I'm going to need to solve the equilibrium expression. However, again, here's where we have to be careful. Remember, this equilibrium point is kind of tricky when it comes to all of this because this was a conjugate acid, meaning that when I write an equilibrium expression, it's going to be a Ka. However, they didn't give me Ka data. They gave me Kb data. So I'm going to have to be very, very careful with how I'm using the data that they give me. So please don't forget, if this is a conjugate acid, you should be writing a Ka expression. And if I write a Ka expression, that's still products over reactants like we're used to. But remember, they gave us a Kb. And specifically, they gave us the Kb of the ammonia, the NH3, which is the conjugate pair. And so hopefully we remember that the Kw is equal to Ka times Kb for a conjugate pair. So if I do a little bit of rearranging here, I can solve for Ka. Ka would simply be the Kw over the Kb. Since the temperature wasn't given, I assume we're at 25 degrees Celsius, which means over here for Kw, I can plug in 1 times 10 to the negative 14th divided by the Kb, which was the 1.8 times 10 to the negative 5th that they gave me in the problem. So this is my Ka value, but I used Kw over Kb. So you could solve that before you plugged it in, or you could plug it in like so. Then the rest of this, I would have x times x, so that would simply be x squared, over the 0.0667 minus x. Of course, we get to ignore that change because our Ka value is going to be very small. And so that gets me an x value of 6.09 times 10 to the negative 6th. So now, what does x represent? Well, yeah, it represents NH3 at equilibrium, but more importantly, it represents hydronium at equilibrium. And so if I'm trying to get to pH, now I can simply just take the negative log of that hydronium ion and solve for my pH, easy peasy. Now, we did say this is the equivalence point. And again, the way we knew it was at the equivalence point is 2 ways. Number 1, I saw that the 2 reactants got totally used up. That was way number 1. I knew I was at the equivalence point. The other way I know I'm at the equivalence point is that all I have remaining is a conjugate product, and that requires me to use the Kw equals Ka times Kb in my calculation. So keep that in mind, that those are kind of the 2 ways we know that we're at the equivalence point here, even if I did not take the time to do a stoichiometry problem before I started. So I can still figure out that I was at the equivalence point. However, what throws people off is the fact that we're at the equivalence point, and as we said, our pH here is acidic. But remember, pH value is only going to be 7 at the equivalence point into titration if I'm combining a strong acid and a strong base. I'm not doing that here. I'm combining a weak base with a strong acid. And so what happens is that because I have this conjugate acid still at my equivalence point, that causes this pH to be ever so slightly acidic. So, substance is present in the solution. Obviously, I have chloride ion. That's my spectator ion. I always have that present. I'm also going to have the NH4 plus 1 present, and because that conjugate acid is present, that is what's causing the acidic pH here at the equivalence point. However, you would have a tiny little bit of ammonia and the hydronium ion. Obviously, here we did create equilibrium, so there's a little bit of that present, which of course is why we get that calculation of the acidic level. However, I would not draw those in a particle diagram at this point. I would only include the chloride and the ammonium polyion. All right, we got one last calculation we're going to do here. We're going to determine the pH when 75 milliliters of 0.2 molar HCl has been added. Now, again, I'm going to approach this from the same standpoint that I've been approaching all the other problems. NDSE, net ionic, dilution, stoichiometry, equilibrium. So to start us off here, net ionic. It's the same net ionic I had before. NH3 plus the hydrogen ion gives me the ammonium polyatomic ion. Then I'm going to do my dilution. First, I figure out my total volume. I had that 100 from the ammonia in combination with the 75 from the HCl. That's going to give me a grand total of 175 milliliters of solution here. So for the ammonia, if I had 100 milliliters at 0.1 molar, what would be the molarity at 175? That's going to be 0.0571 molarity. For the hydrogen, now I have 75 milliliters of that 0.2. So I want to figure out what would the molarity be at 175 milliliters. That comes out to be 0.0857 molarity. So then I look, who's the limiting reactant? Well, I see NH3 is the limiting reactant here. I have less of that, and these are in a 1-to-1 ratio. So that means I'm going to use all of that up. For the hydrogen, I'm only going to use up that 0.0571, so that leaves behind 0.0286. For the ammonium ion, I would end up gaining that 0.0571. Now notice what happens here though. I'm past the equivalence point. So now I have excess hydrogen in my solution. So I can go ahead and calculate pH without doing the equilibrium part of NDSE. Once I'm past the equivalence point, I do not need the E of the NDSE setup. I only need the E before and at the equivalence point. Now, technically this NH4 plus 1 do a little bit of equilibrium where it makes a little bit of H plus, yeah, but that amount is so minor that in comparison to all this hydrogen over here, it doesn't even matter. So I'm going to focus on this hydrogen right here. And obviously, if I have hydrogen ion and I'm trying to get to pH, man, I'm just going to negative log that and get my pH, right? And so I see that my pH value ends up being 1.544. My substance is present in the solution in significant amounts. Again, we see that chloride ion, that spectator ion. I would have hydrogen ion in significant amount, and I would have the ammonium ion, the NH4 plus 1, in a fairly significant amount. Now, NH3, totally gone. I no longer have that weak base. Why? Because I canceled it out with the acid. So now the acid is in excess. All of the weak base I had to begin with has been canceled out and gone away. All right, let's now look at a titration curve for this process. So let's go ahead, flip the page. All right, so what I've done here is first off labeled my titration curve with both pH and the volume of the hydrochloric acid that I'm adding. Remember here, the hydrochloric acid is your titrant. It's what you're adding to the weak base that's in your Erlenmeyer flask below your burette. So the NH3 would have been your analyte. Now, I put on here A, B, C, D to represent the 4 points that we actually calculated. And so then I also kind of addressed what's happening at each of those points. But you notice I used a different color here and here because I want to address some things about the ions in those two particular steps. Okay, so let me come down here and show you a few things. First off, A, that was where we first had that calculation of only the weak base by itself. So that was before any acid was added. And so that's why I needed that initial calculation so I could see where that titration curve started. But then you notice I kind of did this outline here in orange. And that process there represents where the weak base is in a greater molarity than the conjugate acid. So I have a lot of weak base right there, and I'm starting to slowly, surely get it to go down and down and down as I start to add the hydrochloric to that weak base. Now, at point B, this is where we calculated our half equivalence point. And at that point, what happens is that the weak base is equal in concentration to the conjugate acid. That's how we knew we were at the half equivalence point. Also there, remember the pH will equal the pKa. Now, I didn't have Ka, I had Kb, but I could very easily convert it into a Ka, take the negative log of it, and determine what that pH should be. Now, for the next part up here, I put an outline in blue, and that part represents where now the conjugate acid is greater than the weak base. So that weak base is getting smaller and smaller and smaller until I reach the C, the equivalence point that we calculated, where all of that weak base has been completely used up. Now, I marked something else on here, and you might have noticed me marking this on our previous video as well, even though I didn't talk about it. I notated a zone here called the buffer zone. In our next class, we're going to talk about what a buffer is, but in essence, it's where the pH has minor changes even though I might add an acid or base to that solution. It is a solution that resists changes in pH. And so what happens is, because I'm getting this flattening out here, that system resists changes in pH in that zone. And so that means some special things with regards to calculations on that particular part. So we're going to talk more about that in our next class, but I went ahead and had you mark it on here. So again, C here is my equivalence point. You notice we kind of get that vertical shape there to this. Okay, and again, that is the point where we have conjugate acid, but I've used up all of that weak base. It's totally gone. It's been canceled out by the strong acid that I've been adding to it. Now, because I do have excess conjugate acid, that causes the pH at that point to be slightly acidic, even though it's the equivalence point. So remember, the equivalence point is only 7 for the pH in a strong acid, strong base combination. Here, for a weak base, strong acid, it's going to be slightly acidic. If you think back to the previous video when we saw a weak acid with the strong base, it was a slightly basic pH. So we got to be very careful with that equivalence point. And then finally at point D, that was where the strong acid was in excess, and so I didn't need any equilibrium because whatever hydrogen the strong acid was producing, I could use to calculate that final pH. Now, one last thing I want to point out. You notice that sometimes these have a little bit of a curve at the beginning before I flatten out at the half equivalence point. That happens depending on how strong or weak the weak base is. So we sometimes see some variance in shape here with a little bit of curve at the beginning. Don't freak out if you get that. What you should see, though, is a general flattening out here with a general vertical nature at our equivalence point, with then another flattening out here. So again, that kind of classic S shape to our graph. All right, I hope we're feeling pretty good about titration calculations now that we've had not one, not two, but 3 videos on titration calculations. But with that said, hopefully we can kind of see that these worked very similar to the other weak strong combination we saw. We just have a few differences with regards to a weak base instead of a weak acid. All right, if you have any questions or need any help, please feel free to email me. Bye, guys.